Okay, so in lesson number 5, we're talking about thin film interference, and this is kind of like a classic high school physical optics lesson. And basically, it's been done, and you need to know how basically what happens because it explains a phenomenon that we see all the time. And so it kind of builds on our discussion of interference, and this is a special type of interference. So Thomas Young, of course, we saw last lesson, provided some pretty good evidence that light's a wave. And so now we're able to investigate different types of interference, like thin film interference. So one of the things that you've probably observed when you're a kid is that when you blow a big soap bubble from, one of those little things where you get the magic wand, you put it into the soap solution, and you blow bubbles through it, you kind of see this rainbow effect that's in the thin film. Or perhaps on your driveway at home, you've seen oil or gasoline that's kind of spilled on the surface of the driveway, and when the sun hits it in a certain way, it kind of gives you this rainbow. That is thin film interference, and the appearance of those colors tells us that interference is happening, and it's really, really interesting. So this is kind of what you see. You get a thin film of whatever substance, and light comes in and hits that thin film, and some of it reflects off the surface. Some of it, however, is transferred into the thin film and then reflects off of the bottom surface of the film, bounces back up, and emerges. And the interference between these two rays causes different maximums and different minimums to be seen by your eye. Okay? There's also a transmitted ray depending on what that bottom surface is. And so we get an effect. Now, this is a video that I just downloaded from YouTube. You can take a look at it, but here it is. It's basically a film of soap water that's basically on a slope. And so what you'll see is this is a very thin film, and of course this is the effect that we're talking about. And of course, this basically the film is now running. It's on a slope, so that it's basically running down the surface, and so you can see this interference pattern. And this is an absolutely beautiful YouTube video because it really speaks to kind of exactly what we're talking about. So all of these things in here, these would all be at different thicknesses, and so we're seeing different colors interfering constructively at that point. And so it really, really shows nicely what we're talking about. But basically with thin film, some of the light falling on the top surface is reflected, some travels through the film, and then it's reflected again, and we get interference between those two. There's two things that cause this reflection and this interference. So the first is from the path difference. And we know that path difference can create interference because it causes a phase shift. So the path difference between the reflected light, because one of them reflects right away, and one of them travels through the medium, so it actually travels a bigger distance. One of those waves will have a phase shift relative to the other. And depending on what that phase shift is, we may see constructive or destructive interference. And so let's just remember that. So here's our conditions. If the path happens to be an integer number of wavelengths, right, that's m lambda, then we see constructive interference. However, if the path is a half integer number of wavelengths, or m plus a half lambda, we would see destructive interference. So when the light enters that wavelength, we do need to account for the fact that the wavelength, of course, changes when it goes into the new medium. But basically what we're looking for is, okay, that thickness of the film, does it have an integer or a half integer number of wavelengths? And is it going to basically create a path difference that interferes constructively or destructively? Okay, so that's the first thing to keep in mind. The other place that a phase shift can happen is from a reflection. And we talked about this a little bit in grade 11. When a wave reflects off of a barrier, it can either change its phase by a half a wavelength, or it can maintain its phase. And so we investigated this a little bit with springs and used it to apply it to sound. But here, when light travels from a less dense medium to a more dense medium, the reflective ray undergoes a phase shift equal to 1/2 of a wavelength. When light travels from a more optically dense medium to a less optically dense medium, we do not see a phase shift. So this is the same physics that we talked about in grade 11, but now we're applying it to light and we're summarizing it again here. So these two effects, the reflection effect and the path difference effect, we need to keep in mind when we're solving these problems. So when we combine them, basically we're going to get an overall constructive or destructive event. And when we do these problems, there's no formula. Like there's no way to define the behavior in a formula. There's no one system. So what I've done on the next page is that I've kind of prepared some simple steps for you to follow the first few times you're working through some of these questions, okay? And we're not going to necessarily go through them now, but basically, in the first step, we have to determine the number of wavelengths that the incident ray travels inside of the film. So we have to look at the path difference, okay? Now, the velocity of light changes in different mediums, and so because of that, we know that the wavelength changes, and so we need to figure out what the wavelength is in the new medium. So that's kind of the first step. The second step looks at the path difference. If the number of wavelengths above is an integer multiple, then it's the condition for constructive interference. So we could indicate this by writing down a C. If the number of wavelengths is a half integer multiple, this is the condition for destructive. Then we need to consider the reflection. And so we kind of keep a running total. Okay, I've got destructive interference, and now, oh, there's going to be a reflection here that's going to cause a phase shift. Well, now I'm back to constructive interference, and so on and so forth. So use these steps if you want at the very beginning. I'm going to work through a couple of examples now. Okay, so here's example 1. Light reflects off of a thin film of gasoline, N is equal to 1.40, and it's sitting on top of water, which is N equals 1.33. If the wavelength of the light is 560 nanometers and the thickness of the film is 4.8 times 10 to the minus 6 meters, do you see constructive interference, or do you see constructive or destructive interference? All right, so let's draw a little diagram. I've got air, then I've got my thin film of gasoline, and it's sitting on top of water. Okay, so the first thing I need to do is that I need to say, okay, well, light's going to go from the air into the gasoline. So I need to figure out the wavelength of this light, because basically it's 560 nanometers in air. What is that wavelength in the thin film? And so that's what I do. Well, N gas divided by N air is just 1, equals lambda 1 over lambda 2. And so I do a quick calculation here and I say, oh, the wavelength of this light in the gasoline is 4.0 times 10 to the minus 7. Okay? So now I ask myself, all right, how many wavelengths does the light travel as it goes down and back through this thin film? So what's the path length in terms of waves? So how many waves are in that extra little bit of path? Because the first beam hits here and reflects, the second beam has to travel all the way down and all the way back, and then it emerges. So through this thickness in here, we get a path length. Well, how many wavelengths is that path length? So we say light travels a distance of 2 times the thickness of the gasoline. And it goes through the film, all the way down through the film, and then reflects back up. And so what we have is then 2 times the thickness of the film is equal to the wavelength of the film, excuse me, this basically this 9.6 times 10 to the negative 6 meters. So what we'd like to say is, okay, here is the distance that the light has traveled. How many wavelengths is this? And so I say, well, I take this and I divide by the length of one wave, and I get this beautiful number. It works out to 24. And this is the way these questions will work. It'll either end up being a whole number, or it'll end up being a number that has a decimal 5 at the end of it. So it's either a full number of wavelengths, or it's a half number of wavelengths. And so I say, okay, well, because I didn't get a 0.5 at the end here, this is constructive interference. And so far, I've got constructive interference. However, I need to now say, do the reflections at this boundary and at this boundary cause any phase shifts? Because if they do, then that's going to mess this up, and I'm not going to have constructive anymore. So, because the index of refraction here is greater than the index of refraction here, I get a phase shift. And so now all of a sudden, I've gone from constructive interference to now combining this effect up. Now I'm at destructive interference. So let's take a look at what happens down here, because there's also a reflection off of this bottom surface. N3 is less than N2, and so there is no phase shift here. So this first wave comes in, is phase shifted. This second wave comes down, is not phase shifted because of here, and is not phase shifted because of the distance that it travels. We discovered that up here. So we end up getting one phase shifted beam and one not phase shifted beam. And the net effect of path difference and the reflections basically give a half integer number of wavelengths, and we see destructive interference occurs. So that would mean a dark area. This is a template for how you can solve these problems, okay? And we're going to look at many more of them, and we're going to start by looking at this one. Very, very similar. So step your way through this example, but use example number 1 as kind of a template. And in class, we're going to do a whole bunch of different examples. We're also going to work these problems backwards. So instead of saying, does a dark area result, I'm going to start you off by saying, a dark area results, how thick is the film?